some static on it or something.
There's some static, yes.
I have a different earphone system today, and so it's possible that it's not as good as the previous one.
Yeah, there's static on your voice.
Okay, is that that's better?
Yeah, that's
Yes,
better.
better.
Okay, thank you.
Yeah, Dr. Page, I remember for the preceding lecture, I had prepared a few slides to try to, hoping to try to put some light on the Iso-Unit, the connection of Iso-Unit with physical reality. Perhaps we can have it, so 4 or 5 minutes, we can have it scheduled the next lecture with Dr. Georgiev.
Yes,
Yes,
that definitely was a significant question. I think originally from Dr. Guzman concerning the meaning or the physical meaning of the Iso-Unit. And I think for me also that does represent sort of a sort of stumbling block because I see the kind of pictures that you include in your papers, like showing, for example, a deformed ellipsoid, but I have yet to really appreciate how this ellipsoid relates to the isometry, like to the isotopy. And I still have some difficulty understanding the concept of locality that you, in contrast, like say in what we consider to be a usual definition of a function, say between, if you want to make a geometric analogy, like between points on a real line and another set of points on another real line, like we understand quite well what that kind of, what's involved in defining a function. Say a curve in 2 dimensions of a particular kind is a kind of geometric picture that we might associate with a function. But I don't have that same kind of geometric picture related to what you've been calling an isofunction. So I still have a feeling that I'm missing some fundamental intuition.
No, I think you're absolutely right. The Iso-Unit, I think, is extremely important because it really changes the geometric significance of all the elements in the algebra as well. So I think it's extremely significant to what exactly there should be a geometric interpret. What does this isotope mean? That's the whole question.
Well, all those questions are very fundamental and absolutely legitimate indeed. You know, there's a very legitimate question, and it is the fundamental notion. In Dr. Georgiev books, you will not necessarily see the treatment of isotope. You will see the treatment of the isotopic element, but you know and he writes rather than writing the Iso-Unit, he writes 1 over the isotopic element. So the notion of Iso-Unit is reducible to the isotopic element, and that I prepared those transparencies. Maybe next time, and not because now the Dr. Georgiev's lecture, and basically the connection is I want to show is that the connection all the way to the Newton's equation, with the Newton force divided in self-adjoint and non-self-adjoint. Namely the derivable from a potential and non-derivable contact forces, you know, resistive forces and so on. And then go all the way through Lagrangian Hamilton real equation, variational principle. This to show where Dr. Page, also another important question, can the isomathematic, can the optimal control theory extend to include optimization of a surface or a shape within the resistive medium? I believe this was your important question.
I had a relatively elementary question, I think was my first question, which was an example from aerodynamics or even fluid dynamics, And I think it related very closely to Dr. Guzman's comments about the continuum mechanics.
Yes.
Yeah, so the point being that all of fluid dynamics, to my knowledge, has been developed with conventional calculus. And that when we write down like the Euler equations for fluid and so forth, we're doing that with conventional calculus, but we apply the conventional calculus to problems of involving extended bodies, such as an airplane wing. So I see that as somewhat contra the statement that conventional mathematics is inadequate in some way. And so I'm trying to see how the extensions that you've proposed, say in isocalculus, how isocalculus could be somehow a better tool for describing systems such as those that are currently described in fluid dynamics.
Yes, there are a number of publications, and that one important one is on mathematical foundation, mathematical methods in physics. But the answer apparently the apparent answer is yes, there exists, because the iso action, well, the iso variational principle is universal in the sense that it represents not what we call the truncated Lagrange and Hamilton equation, those without external term. No, it represents Lagrange and Hamilton's equation with external term. The external terms are essentially embedded in the Iso-Differential Calculus. And once you do that, automatically you achieve what we call direct universality for any ordinary differential, and for all infinitely possible Newton's equation. And that I would like to show you, that was a part of my few minutes. We can do this next week and dedicate it to all those aspects that are, if you agree, of course.
Yeah, I think it's definitely important from the point of view of intuition. Perhaps Dr. Georgiev has some things to say that would allow us to develop a better intuition of what is involved in isocalculus, say through what you've been referring to as sort of an iso-differential geometry. Maybe that would be some way of providing a greater intuition. But I do worry that very often, for me anyway, the papers that I've read so far start out fine with pictures that I understand and a bit of intuition that I understand, but go very quickly into more advanced applications. So for me, seeming to skip several steps, at least in my sort of conceptual development of what's going on. So I worry that if we skip too directly into advanced differential geometry, that I'd still be missing that link, the intuition. That
was my proposal also for the past week, for the past meeting. But from unfortunately, I sense a different way of perception of isomathematics from a mathematical viewpoint and from a physical viewpoint. From a mathematical viewpoint, what are important are the basic axioms, and that's it. And then realization are essentially the infinitely possible realization that essentially is a physical problem or an applied problem more than a pure mathematics. So from an axiomatic viewpoint, Isounit is a positive, definite quantity period. It can be an infinite number, an infinite number of possibilities. And however, from an applied viewpoint, so I would like to ask to be lenient on Dr. Georgiev, because he is a pure mathematician. He's a magnificent pure mathematician. And remember, Dr. Dr. Cruz, you ask, Dr. Georgiev, you ask, what is the ISO unit? He answered correctly. It's the inverse of the isotopic element. It's a positive definite quantity. That's the axiomatic definition. What it is,
No.
to use a realization. Then you have to enter into specific realization to get. But there are an infinite number of realizations. This is the issue. Depending.
Let me ask one point. Why do you insist that it's positive definite? That's physics applications, but any invertible element, I would suppose, can be an ISO unit.
But my question is in the side of mathematical object. That is, if I think that the ISO unit is related with the field of the scalar fields, for example, no? Then I can give one interpretation to this. But if I think that it is in the another type of mathematical objects, for example, vectors or multivectors of something like this, I can give another kind of interpretation, and I need to understand where is the axiom. Where is the axiom? If the axiom is in the field of real numbers, or if the axiom is in the scalar field of functions, or if the axiom is in the maybe in one module of this or something like this. I am trying to understand that, because this is fundamental for all the foundation of the theory.
Well, why don't we schedule the session and next week. Yeah. Dr. Subject, you had a very deep, correct statement. You made a statement that the ISO unit can be any invertible quantity. That is very, very true. Because the only thing that's required is that the quantity be invertible, so that it admits an isotopic element. The reason why we are restrictive and assume to be positive definite, because if you relax the condition of positive definite, then you look at the algebra, which is characterized by this new numbers that we call Geno numbers, then the algebra becomes Lie admissible. So, and this, you pass from physically from the representation of stable, permanently, stable systems, such as a stable nucleus that will resist forever. You pass from the representation of those structures to a representation of nuclear reactions that are irreversible over time. So it's a kind of a restrictive, I never mentioned, but I'm so glad that it did not escape your attention, Dr. Subject. Thank you. This is part.
I can understand that from a physics point of view.
But the numbers are called Geno numbers.
Saying it's positive and definite.
But then you have complex value, and then becomes the intuitional intuition. If you have difficulty now on the ISO number, when we go to the Geno number, the difficulties are multiplied. I think we should first solve at least try to reach an understanding with the ISO number, and then pass to Geno number, and perhaps hyper number, and perhaps iso-dual number.
Okay, well, perhaps we could invite our main speaker, Dr. Georgiev, to give his presentation that he planned for today. And if you can make any comments, side comments or related comments to these questions, I think that would be appreciated by everyone.
Okay.
Dr. Georgiev.
Thank you very much. Today we'll continue the previous lecture from the previous Previous week, we consider what is isoline, the basic equations of isoline, perpendicular isolines. Today, we will continue this with isoperpendicular isolines. Two isolines are said to be isoperpendicular if their isodirection isovectors are iso-orthogonal. So as a first example, we'll consider for the first isotopic element hat T1 to be equal to 2, for the second isotopic element to be hat T2 equal to 3. We take 2 points P and Q and take two vectors V and W. Then we find the corresponding isolifts of the given points P and Q. Their isolifts are the points hat P, which is given in this way, and the point hat Q, which is given in this way. Then for the vectors V, we get its isolift to be this vector, and the isolift of the vector W, which is hat W, is this vector. So we have to investigate firstly if these two vectors are iso-orthogonal. In our case, they are iso-orthogonal. And we have that these two isovectors are isoperpendicular. Now we suppose that hat L is an isoline through the isopoint hat P with isodirection isovector V, and hat M to be an isoline through the isopoint hat Q with an isodirection isovector hat W. Then the equation of the isoline hat L is given in this way, and the equation of the corresponding isoline of the line M is given in this way. Both isolines, hat L and hat M, are isoperpendicular. In the next figure, we show in the green color the isoline hat L, and in the brown color the isoline hat M. As next example, we'll consider the case when we have two orthogonal lines, but their isolifts are not iso-orthogonal. As first isotopic element, we take hat T1 to be equal to 1, hat T2 to be equal to 2.
Let me just say one thing. For each dimension, we have a different ISO unit then for, in this case, T1 hat, and then we have I1 hat and so on. We have different ISO units for every dimension, and if I understand correctly.
Yes, see, we can take as isotopic element different definite positive operators, but we can consider in the cases when this positive definite operator is the identity. In our case, if it is equal to 1, then in the one direction, we have the real line, and in the second direction, we have isoline, okay? When the isotopic element is equal to 1, then we get the classical case. When the isotopic element is different than 1, then we get the iso case. Here is considered a combination when the one dimension is the real case and the second dimension is the iso case. To see what happens. Because all classical differential calculus and all classical calculus with the numbers, we can consider as iso calculus in the case when the isotopic element is equal to 1. Then there are possible examples in which one of the isotopic element is equal to 1. But in many of the examples, the isotopic element is different than 1. Here, I only give example when the, to say x-axis is the real x-axis and y-axis is the iso y-axis combination. Okay?
So
yes,
when you draw pictures of isolines, such as you did in the previous slide, how should we interpret this? Like, So to me, when I look at these naively, I see, two lines on, and if I imagine an axis, they look just like lines I would have in any sort of Euclidean geometry. So I don't, what in this picture, what about this picture suggests that I think this picture is intending to be perpendicular. So if I interpret it in ordinary Euclidean space, these lines don't look perpendicular, right?
But see, these lines in the real case are not perpendicular. With this example shows that the real angle has to be different than p over 2, but they are at the same time iso-orthogonal. If we continue this line, we see that the angle is not p over 2 here. Then the corresponding lines, real lines, are not orthogonal. But if we consider as iso lines in the iso case, they are iso-orthogonal.
But if I were willing to change the basis, so if I were willing to say that I'm not dealing here with orthogonal Euclidean space, but I have a basis for the space which is skew in some way, then the kind of drawings that you are making here are like the kind of drawings that I would see if I was drawing a picture using a non-orthogonal basis.
But in the previous lecture, we saw that if in the Euclidean case we have basis, in the iso case it is not basis. Many examples I give in the previous lectures where we saw that we have linearly independent system in the classical sense, but in the iso sense it is not isolinearly iso-independent. Then if we have a basis in the real case, in the iso case it is not always basis, and conversely.
Let me give you an example that we found often in physics. This is an iso-Euclidean space in 2 dimensions, iso-Euclidean, with one single, the cases with one single isotopic element, which is, however, is a matrix, the diagonal, so has 2 elements, so it's somewhat different. So on the iso-Euclidean space, we represent the iso line as being really perpendicular, but careful that will be the iso angle, which is the product of a physical angle multiplied by the iso unit of the angle, which is different there. Then the iso angle is 90 degrees. However, the projection of those 90 degrees intersecting iso line and when you project in an ordinary Euclidean space, then the angle is arbitrary. It depends on the iso units value and so on. So
yes. Yes, obviously, here the angle is a classical angle divided on the this iso units head T1 multiplied by head T2 and so on. Then if an angle is acute in the classical sense, it can be not acute in the iso case. It depends on the isotopic element. For instance, if the isotopic elements are less than 1, then in the classical case, we have acute angle. In the iso case, it is not acute angle. The angle is greater than p over 2.
yes.
Okay. Okay. Here is a picture where we see, if we consider these lines as classical lines, here the angle is not p over 2, but iso angle, because it depends on the isotopic elements, these lines are iso-orthogonal. Okay?
Okay, for now, yes.
Okay, next example here, we consider the isotopic element 1 to be equal to 2, the second to be equal to 4. if we consider these two vectors v and w, these two vectors are not orthogonal in the classical case. If we compute directly 2 multiplied by 4 plus minus 4 multiplied by 16, it is different from 0. These two vectors are not orthogonal in the classical case. But if we make isolift with respect these two isotopic elements, head T1 is equal to 2 and head T2 is equal to 4, then the corresponding isolifts are this one. And using the rules for iso inner product, we get that their iso inner product is equal to 0. And these vectors are iso-orthogonal. Corresponding lines L and M, L corresponds to the vector V and point P, M corresponds to the point Q and the vector W, and their isolifts head L and head M are iso-orthogonal, but the lines L and M are not orthogonal. And in this picture, we see the picture for the iso lines. In the green color is the isoline head L. In the brown color is the isoline head M. Here, angle is greater than right angle. But these two lines,
have two different
yes,
iso units involved. So we're
yes,
really, it almost seems like we're comparing two different scales then, because one is 1/2 and the iso unit's 1/2 and the other is 1/4. So does it make sense to be comparing with different iso units, whether a line is
yes, yes. See, we saw cases in which taking 2 points, but if we take one combination of iso units, the corresponding line are not iso-orthogonal. But if we change the isotopic element, then we can obtain iso-orthogonal lines. In other words, the iso-orthogonality depends on the iso units. There are cases in which 2 iso lines are not iso-orthogonal with respect a combination of iso units,
So maybe you
but
could define
at
an
the
iso
same,
unit as a tensor product or something. So you still have only one iso unit that are, rather than
yes,
defining.
here the iso unit is one is the 2 is equal to 2, the second is equal to 4. In the previous case, we take iso unit head T1 to be the classical unit and head T2 to be equal to 2. Then we get this situation.
Yeah, in our, Dr. Georgiev, in our physical formulation, those 2 and 4, we call N1 square and N2 square. And,
yes, but when we consider head M1 square plus head M2 square, then it is equal to M1 square over head T1 plus M2 square over head T2. Again, depends on this iso units head T1 and head T2. And if we take these iso units to be less than 1, then this sum of the iso square increase. If we take the iso units to be greater than 1, then the sum of these squares decrease.
yes, your formulation.
And then this iso-orthogonality depends on these isotopic elements.
Let me just clarify, because the colleagues have seen some physical paper. Doctor, in our physical application, we restrict the value of the elements of an iso unit to be positive definite. Dr. Georgiev is presenting you a formulation much more general. Dr. Georgiev is a mathematician, so he's presenting a much more broader formulation in which, in other words, his presentation cannot be reduced to the n1 square and 2 square and so on. No, because n1 square is being introduced to be positive, for the intention to be positive definite for physical application. But it's from a mathematical viewpoint, this presentation, of course, its presentation includes a particular case. when the elements are all positive, our physical application. This is treated in volume 2 of my Elements of Hadronic Mechanics. But however, it's much more general. So thank you, Dr. Georgiev, to be a mathematician and show them how broad isomathematics is. Thank you.
But
Okay,
can I also just point out that this is a question closely related to what Dr. Sobchak mentioned in sort of our introduction, is that I would consider these two iso units as being sort of elements of a diagonal representation of some mapping between two space. So in the case that Dr. Sobchak mentioned, he said, well, the iso unit is the matrix. So he was talking about the invertibility of the matrix. So of course, there is no question about the invertibility of a diagonal matrix, but the iso units seem not necessarily related to, like the iso unit seems to me doesn't necessarily have to be diagonal, right? So that we could have relationships between, so in this two-dimensional case, a relationship between one axis and another, right? So off-diagonal elements in the iso unit.
But see, I think that it is not possible to find general representation of this map from the classical into iso case, because in sometimes these elements had U1. It depends if we have a square or other power function. It reflects on the corresponding object in one way. If we take other classes of isotopic elements, they reflect in other way. Then some general representation of this map from real Euclidean case to iso case, for me, it is impossible. It depends on the considered object. And I think that for every one class of objects, we have to make computations, because now we see isoline what is. But later we will see in this lecture what is isotranslation and what is isosymmetric point. They are very different, and it depends, their finding, it depends on the isotopic element, but there is not strong law how to find this dependence. We have to make computations for every one case.
Yes.
Yes, I understand Dr. Savchuk that he suggests to find some general formula so that taking an object from the real case, applying this general formula to get the object in the iso case. For me, it is impossible because it depends on the objects. We can find such mapping, but for subclasses of objects, not for all classes. As I explained to Santilli, that the sum of the square when the isotopic elements are less than 1 increase, and when they are greater than 1 decrease. In other cases, we have other combinations.
But
then for every one class, we have to compute. Yes?
The examples that Dr. Sobchak probably has in mind, I think, would come, say, from what he terms geometric algebra or Clifford algebra, where we can choose an element of the geometric algebra as an iso unit, but that element doesn't necessarily have a diagonal representation, like in. If we were to represent the geometric algebra as an algebra of matrices, then the iso element does not necessarily have to be diagonal.
Of course, any symmetric matrix, by choosing a basis, can be reduced to a diagonal matrix. So in a way,
but not in any case diagonal matrix.
Gentlemen, please let me make one point. Dr. Page, your point that isounits can be non-diagonal is absolutely correct. In certain physical cases, it's necessary. For instance, this is the case that there is various literature for the representation of the experimental data of the so-called Bose-Einstein correlation. This is proton antiproton annihilation. In that case, the ISO unit had to be two-dimensional for the first characteristic function, but the two-dimensional necessarily had to be non-diagonal in order to represent to have an exact fit of the experimental data. If you are interested, I'll send you the paper. There is a paper here in America and a paper published in Russia as well. I'll be happy to send them to you.
Okay, thank you.
Okay. That's we saw these examples when we have perpendicularity and not perpendicularity. Now we will mention the following properties of two elements of the two-dimensional iso space. If we take two elements het x and het y, then we have the following equality. So I note that here the multiplication is the classical multiplication. It is not the iso multiplication between het 2 and the iso inner product between het x and het y. So, and we have the using that here the multiplication is not iso multiplication, it is classical multiplication, but the powers are iso powers, and here the inner product is iso inner product. Then we can deduce the iso-Pythagoras theorem in this way. That if we take three distinct iso points het P, het Q, and het R from the two-dimensional isospace, then we have this equality if and only if these two isovectors are iso-orthogonal. So now, if we suppose that the isolines het L and het M are two isoperpendicular isolines, then they have a unique isopoint in common. As next example, we consider here the isotopic elements are less than 1. The point P is the point -1, 0. The point Q is 2, 1. We take the vectors V and W to be this one. Then the corresponding their isolifts is het P, het Q, which are given with this expression. For the vectors, we get these vectors, het V and het W. And as I have explained in the previous lecture, previous week, if we take two vectors, then we have to find the corresponding iso-direction, iso-vectors of the corresponding isolines. In our case, the iso-direction isovector for the first isoline het L is given in this way. It is obtained from the isovector het V, and the isodirection isovector for the second isoline het M is derived from the isovector het W, and it is this vector. From here, if we make the direct computations, we get that the iso inner product is equal to 0. Thus, these two iso-direction isovectors are perpendicular. If the equations of the isolines het L is given with this equality, and the equation of the isoline is given with this equality. In this case, we have again that both lines het L and het M are iso-orthogonal. Now we'll find the unique common isopoint of these isolines het L and het M, because we get that the isolines are isoperpendicular. Our last theorem says that this isolines has unique common isopoint, and we'll find this isopoint using this system, and this unique isopoint has the following representation. In this figure, they're depicted the two isolines head L and head M. Again, we see that this angle is not orthogonal. It is not P over 2. It is close to P over 2, but it is not P over 2. Then the iso lines are isoorthogonal, but the classical lines are not orthogonal. As next example, we take for the first isotopic element to be 1 over 4, for the second isotopic element to be 1 over 2. We take 2 points P and Q and 2 vectors V and W. Then their isolifts head P is given with this point. The isolift of Q is given with this one. The isolift of the vector V is this one, and the isolift of the vector W is this one. The corresponding isodirection isovectors are given with this expression. This is for the isoline head L. This is the isodirection vector for the isoline head M. From here, after we make the direct computations, their iso inner product is equal to 0. Then again, both lines head L and head M are iso-orthogonal. Their equations is given for the isoline head L is given with this equation, and for the isoline head M is given with this equation. Both isolines are iso-orthogonal, and their unique common iso point is the point 2 over 5, 8 over 5. In the next picture are given both lines. Oh, excuse me. This one. Again, we see that the angle is not P over 2, it is other angle. And as third example, we consider that the isotopic element first is 1 over 6, 1 over 2. The first point P is 1, 1. The second point Q is 0, minus 1. We take 2 vectors V and W, and their isolifts are given with these vectors. Then we find the corresponding isodirection isovectors, which are expressed with this one and with this one. From here, making the detailed computations, their iso or inner product is equal to 0. Then both lines, isolines, are isoorthogonal. The first isoline have this equation, and the second isoline have this equation. Their unique common iso point is the point 1, 1, and in the next picture they're given. Here is very small. In the red is this line, in the brown is this line. So in all these examples, we consider in this example the isotopic element, both isotopic element are less than 1. In the previous example, again, the isotopic element was less than 1, and in this example, again, the isotopic elements are less than 1. When the isotopic elements are less than 1, we will see in detailed proofs later that the iso angle between these isolines it is less than P over 2. But when the isotopic elements are greater than 1, as in this example, here the first isotopic element is 2, greater than 1. The isotopic element is the second isotopic element is 4. The classical angle is greater than the right angle. But when the isotopic elements are less than 1, we have acute classical angle. But this acute classical angle corresponds to iso right, iso angle.
So can you relate that, for example, in relativity on the in hyperbolic geometry, the angles are changed as well? Can you relate that to hyperbolic geometry or anything like that?
So we see that to speak for the isospherical and isohyperbolic geometry, we will see that we have a need of some additional definitions for inverse isotrigonometric functions, because in the end of this lecture, I will give some isotrigonometric formulas, and you will see big difference with the classical formulas. Then after we define new isohyperbolic functions, then we will get other isohyperbolic geometry and isospherical geometry. Because in the classical case, if we consider circle or sphere, this corresponds for they looks at as ellipse in one case, and in some deformed sphere for the isosphere. But this we will see in the next lectures. Then again, we can find general formula so that to compute if we have the classical angle between two lines, classical lines, to find a general formula so that to compute the iso angle between the iso lines, because we see that if the isotopic elements is less than 1, we have classical acute angle. If the isotopic elements are greater than 1, we have angle greater than the right angle. If we find a combinations of the one isotopic element to be less than 1, the other isotopic element, second isotopic element to be greater than 1, then we get different nature. And this is the reason for which we cannot find a general formula, so that to move directly from the classical case to iso case, and from the iso case to the classical case.
So can you relate the geometries with a mapping or anything like that between these different geometries? There's so many of them. There's infinity of them.
Yes, different geometry, and we'll see in the next lectures that it reflects and on the infinity and non-infinity. We'll see difference, because if we consider the functions 1 over x classical function, and we take x to be close to 0, then we get infinity. But the corresponding isolift at 0 is not infinity. And there is not a general map, so that to say here classical case we have infinity, in the iso case not infinity. Then we have to compute in every situation what happens. Okay, now we take an isopoint head R to be arbitrary, and an isoline head L arbitrary. Then there is unique isoline head M that is isoperpendicular to the isoline head L, and this isoline head M can be represented with this equation. The above isolines head L and head M intersect in the isopoint head F, and the intersection points is given with this representation. We say that this representation is different than the classical representation, because here we have iso multiplication. From the iso multiplication, it is appear the corresponding isotopic element. And again, if the isotopic element is less than 1, then the distance from the point to the line if decrease, and in the other case is increase, because the sign minus. So, and the distance, the formula for the distance, iso distance between the this above points head R and head F is given with this formula. Now we'll give some examples. So this number head D is said to be iso distance from the isopoint head R to the isoline head L. We take for the isotopic element het T to be equal to 2, het T1 to be equal to 3, and het T2 to be equal to 4, 2 points R and P, which are this one, and for the vector V. Firstly, we will find the classical equation of the line L through the point P and with direction vector V, and its equation is given with this equation. Then we find the classical line M that is perpendicular to the line L, classical line, through the classical point R. Their intersection points, these classical lines L and M, are classical perpendicular, and their intersection point F is given with this point, -1, -1. The classical distance between the point R and the line L is 2 power 1/2. This is the classical distance. Now we will find the corresponding isolifts for the point R and for the point P and for the vector V. Then the
Can I ask you just one technical point for clarification? The symbol colon that you have, say here, what does that mean, that colon symbol?
I say I have you this double point.
Yes.
Or het. Yes, this is the classical notation when we have to express that this line has this equation. We use this in classical geometry when we say that some object, line, surface, and so on, the notation for the corresponding object, in our case, line, 2 points, then the corresponding equation. This is classical notation. Okay.
It's just naming that line L hat, that's all.
Then het L is here the line.
Okay.
Okay. Yes.
Not immediately clear to me, the meaning, but
What?
just
to say that some iso line has equation, we will use this notation. Here on the left, we write the notation for the line here, then 2 points, then the equation of the iso line. Again, we can see for next line, this het M, then 2 points.
Oh, okay. Okay. Now I'm reading it. It's just a matter of how to read it. So this is just a definition of the line.
Yes.
It
Notation
just
for
means L is defined as that.
No division. This is notification for the equation of a line. Okay. So
equation, that's all saying.
yes. So the classical distance between F and R, we get this number. Now, after we find the equations of the iso line het L and het M, and after we compute this vector het N, then the intersecting points is given with this one, and the distance, iso distance, is equal to this number, square root 7 over 96. This is iso distance from het F to the line het L. In the classical case, classical distance is 2 square root 2. Okay, the intersecting point classical is the point -1, -1. After we do all iso lifts, the iso intersecting points is this one. Very different. Also, here the iso distance is square root 7 over 96. It is less than 1. But the classical distance, which is this one, is greater than 1. Here is given the picture. In the green and the red color are given the classical case. In yellow and brown colors are given the iso case. So as next example, we consider as isotopic element hat T to be equal to 5, the first isotopic element to be equal to 2, and for the second isotopic element to be equal to 3. Take two different points R and P to be these points. For the vector V, we take this vector. Then we compute the classical equation of the classical line L, which is this one. We find the normal vector, classical normal vector to this classical line, which is this vector. Then the equation of the classical line M, which is perpendicular to the classical line L through the point R, is this one. And their intersecting points, classical point, is this one. Now we will see for their isolifts. So the classical distance now is this number, 7 multiplied by square root 5 over 5. Now we'll compute the corresponding isolifts. The equation of the isoline hat L is this one. Its isonormal isovector has these coordinates. And the equations of the isoline hat M, which is isoperpendicular to hat L, is this one. Their intersecting points, iso point is this point. This point is different than the previous point, which was this one. This is the classical. This is the iso point. They are different. The iso distance between the point, the iso point hat F and the line hat L is this one. This number is very different than this number.
Excuse me, if I made one exercise with these questions that you are using, not in the coordinate form or representation, but like vectors, for example, for the lines. And I have to first to translate to isobectors, and then we can get the right line equation.
Yes, yes. In the previous lecture, I have given a way how to, if we take a vector, classical vector, for the direction vector for a classical line, how to find the corresponding iso-direction iso-vector.
Yes,
yes, and using this iso-direction iso-vector, how to deduce the equations of the corresponding iso-line. Yes, please.
Okay, and I am going to get the same results.
Yes, yes, I can send you the exact file from the previous lecture. Previous week, I have given explicitly how to compute these equations, hat M and hat L, because hat L is this equation and L has this one. They are different. One is 4 over 3x1 minus 7 over 3. Here is 2. Yes.
Excuse me, but for example, in here, the next slide. Okay, here we have a M hat, no?
Yes.
M hat is in vector form. Maybe we can put like one iso-vector, I suppose, that is minus 3
Over 4.
over 4 came 1. No?
So here, when we have ISO unit multiplied by some object is equal to the object. ISO unit multiplied by x is equal to x. But ISO unit is het I, or het I1, or het I2. In this case, because we have in front of the second variable, we will have as a coordinate het I2. And the other coordinate will be minus 3 over 4. Okay.
But Jesus, do you mean to write this in a coordinate-free form, like to write it using just vector notation without any reference to coordinates?
Yes.
Yes.
This is the idea. I am not sure that if I translate to coordinate free form, I am going to get the same equation.
Yes, but see, I will send you a previous lecture from the previous week where given how to find these equations. And then you will compute using the previous lectures formulas.
Okay.
You compute and then you will compare with this equation given in this lecture. Okay.
Okay. Thanks.
In the book, which is
maybe it'd be more interesting to study iso rotations or something like that. Just looking at the intersection of these lines doesn't really give any insight into much of anything, I don't think.
Yes, very different. And they're studied in big details in the book, which will appear maybe June. Iso-Analytic Geometry is the next book, and it will appear in June this year. It is under press, but I can send you the files where in details are proved and investigated all properties. Okay?
Okay, thanks.
Okay, so we see this distance. The pictures here, green and red is the classical case, and yellow and brown is the ISO case. So next example, we take for the isotopic element to be 4, first isotopic element to be 2, second isotopic element to be 5, take 2 points R and P and 1 vector V. Using the classical case, for the classical line L, we have the following equation. For its normal vector, we have this vector. For the equation of the line M, which is perpendicular to the classical line L and passes through the point R, we get this equation, and their classical intersecting point is this one, F. Now it is computed the classical distance from F to L. Classical is this one, and now they are given the corresponding isolifts of the point R, it is het R, of the point P, it is het P, and it is equal to this one. Of the vector V, it is this het V. The equation of the isoline het L is this one. It is different than this one. For the isonormal vector for these isolines, for its coordinates, we get this number n1 and n2, and then we deduct the equation of the isoline het M, which is isoperpendicular to this isoline het L. After this, their intersecting isopoint is this one. It is different, and the iso distance is this one. In our case, is this number, iso case. In the real case, is this number. Very different. And for the intersecting iso point, we get this one. for the intersecting classical point, we get this one. Again, different. Here is given the picture. In green and red colors are given the classical lines L and M. In the yellow and brown color are given the corresponding iso lines. So now we'll give a definition for isoparallel lines. Two distinct iso lines, head L and head M, are said to be isoparallel if they have no point of intersection, and to give this notation. As example, we take for the isotopic element head T to be equal to 3, head T1 to be equal to 3, head T2 to be equal to 9. Then the equations, classical equation for the classical line L and M are this one. And their isolifts for the classical line is head L. We see here in one side that this equation is very different than this one. And for the equation of the isolift of the classical line, this M, we get the corresponding iso equations, this one. This equation and these are different. Both iso lines are parallel. So here is given in red color is given the line L. In blue color is given the classical line M. Red color and the blue color are parallel. In green color is given the iso line head L. In brown color is given the iso line head M. They're iso parallel. Here are given investigation for the coordinates of the isoparallel isovectors. And after we have defined isoline equation of isolines, perpendicular, isoperpendicular isolines, isoparallel isolines, we will define what is isoreflection. So now suppose that head L is a given isoline. The isopoint head X belongs to some set V, but not belongs to the this isoline head L, and suppose that this vector head X head F is isoorthogonal to the isoline head L. Also, this vector head N will be the isonormal vector to the isoline head L, for which we have the following condition. N1 square over head T1 square plus N2 square over head T2 square is equal to 1. This is the basic condition when we have an isovector to be isounit vector. So now here is very convenient place where you can see if in the classical case we have a unit vector, then the corresponding isovector is possible to be not isounit vector because these isotopic elements have, oh, excuse me, because the participation of these isotopic elements head T1 and head T2. So, and now we define the point head X prime, which will be called the symmetric point of the point head X with respect to the isoline head L. The symmetric point is given with these coordinates. Now we'll give a formula for the for its coordinates, and we obtain the following representation of the point head F, which is given with this one. It is different than the classical because here we got iso multiplication. And for the isosymmetric point of the isopoint head X with respect to the isoline, we get the following representation. Again, this representation is very different because here we have one iso multiplication, here we have second iso multiplication, here we have isounit iso vector. After this, we define the following operator, which of any point, any iso point at X map to the corresponding its isosymmetric iso point at X prime. Now I will give an example. If we take for the isotopic element head T to be equal to 2, head T1 to be equal to 3, and head T2 to be equal to 4, we take an isoline which passes through the isopoint head P with isonormal isovector head N to be equal to be this vector. For an isopoint, we take this point. Then we find the corresponding iso-unit vector, which is this one. We find this multiplication, and in the end, we find the isosymmetric isopoint of the isopoint head X. It is given with this expression. So as next example, we take for the isotopic element to be head T to be equal to 3, head T1 to be equal to 4, head T2 to be equal to 2, for the points P to be this point, for the points X to be this one, and for the vector V to be this vector. The classical symmetric point X prime of the point X with respect to the line L is this point. This is the classical point. Now we will find the corresponding isolift. The corresponding isolift of the line L is this one, and of the point head X is this one. We see that the isosymmetric point of the point of the isopoint at X is this point, which is different than this point. This is the classical symmetric point. This is the isosymmetric point. So as next example, we take for the isotopic head T1 to be equal to 6, and for the second isotopic element head T2 to be equal to 2. For the point X, we take this point. For the point P, this point, and for the vector V, we take this vector. The classical line L through the point P with direction vector, we get this equation. And for the symmetric point, classical symmetric point, we get this point. Now it is given the equation of the isoline head L, and the isosymmetric point is given with this expression. We see that this point, isosymmetric point, is very different than this symmetric point. So now I'll give some of the properties of the definite operator. First property that if we apply both times this operator to arbitrary point at X, we get the same point. We get that as a second property that if we apply the operator L on the point at X, and if the map is the same point, then the original has to line on the isoline head L. The iso distance between the iso maps is equal to the iso distance of the iso originals. The definite operator head omega head L is a bijection. Now I'll give a definition for an isoisometry. A mapping head A is said to be an isoisometry. We have if the following condition hold. So I will not, because here in the definition participate iso distance. If we have an isoisometry, in the classical case, it is possible to be not isometry. Then two iso figures head F1 and head F2 are said to be isocongruent if there exists an isoisometry. Excuse me. So that the map of the iso figure head F1 to be equal to and to coincide with the iso figure head F2. The defined isoisometry is bijection. If we have two isometries, then their multiplication is isoisometry. The set of all isoisometries form a group, and this group will be called isoisometry group. And this iso group will be denoted in this way. Now we take het F to be an arbitrary iso figure. The set which is defined in this way is a subgroup of this set, and this set will be called isosymmetry group of this iso figure het F. So now we will give a definition what is isotranslation. We take two isolines het M and het N, take two isopoints het P and het Q. We take isounit vector het N to be this vector. Then the isotranslation translation of the point X is defined with this equality. Again, we have a difference with the classical case because we have two isomultiplication. Here is the first isomultiplication, and here is the second isomultiplication. Also, the corresponding isounit isonormal vector in the classical case is possible to be not normal vector. This map het omega het M het omega het N will be called isotranslation. The set of all isolines isoperpendicular to a given isoline het L is called isopencil of isoparallels. Yes.
If the translation can be non-linear.
Yes.
Because that's what we found in the isotope with the Poincare symmetry, the translation, they are indeed non-linear and the various.
Yes, it depends again on the isotopic element.
Yes, yeah.
So here are given some of the properties of the isotranslation. The isotranslation with respect to the isodirection vector will be denoted in this one. And if we take an iso direction vector and define the map in this way, then we get isotranslation. For any three applications of this operator het omega, there exists a unique isoline het delta, so that these three applications to be represented with this operator. Here is given that for any two applications of this operator het omega, we can find other representative, not only het alpha and het beta, other representative, so that we have to have equality het M and het M prime, het N and het N prime. Here are given some expressions of the applications of these operators, of both applications of this operator het omega can be represented with the isotranslation. This isotranslation combination of isoreflection and isotranslation is given with isoreflection. This isoreflection, a combination of isoreflection, isotranslation, it is given with this isoreflection, and combination of two isotranslations we get this isotranslation. We define denote with the set het T to be this set with the vectors. And now I'll give an example that we take for the isotopic element het T to be equal to 3, het T1 to be equal to 4, het T2 to be equal to 2, for the point P to be this point minus 1, 1, for the point Q to be this point 1, 1, for the point X to be the point 3, 4. Then the classical translation is given with this point, but the isotranslation is this point at X prime. This point is very different than this point. So as next example, we take the first isotopic element and the second isotopic element to be less than 1. For the points P and Q, we take these 2 points. Excuse me, P to be this one, Q to be this one, for the point X to be this point. Then the classical translation is given with this one, but the iso translation is this one. This iso translation point and this translation point are very different. Iso inner product is given with this one. This is iso inner product. This is the corresponding classical inner product. So in the next example, both isotopic elements are greater than 1. For the point P and Q, we take these 2 points, and for the point X, we take the point 0, 1. Then its classical translation is this point, but its iso translation is this point. This point and this point is very different. So now, before to define isotrigonometric functions, we have a need of some sets with several iso units. Suppose that het T is positive, het G is positive, and we define het F to be the union of these sets. And in this set, we define 2 operations, iso multiplications and iso division in this way. If we have elements from one isospace, the iso multiplication is as it is defined the iso multiplication by Santilli. The iso division is as Santilli is defined iso division. Here with a constant is defined in this way, but one moment, when we have multiplication, iso multiplication between 2 elements which belongs to different iso spaces. This element belongs to the isospace het F, het Tg, and this to het F, het Tk. Then iso multiplication defined in this way, iso division in this way. For 3 elements, we define iso multiplication in this way. Yes.
Preceding slide, I missed it. I missed the definition of the division.
This one.
Yes, I missed it. Just a moment. My eyes. Okay, now I can see it better.
Okay. Yes. And then we define iso multiplication between 3 elements this way, iso power in this way. We see that we have the following example. If we take 3 isotopic elements 4, 2, and 3, and if we consider all of these elements 3, het 4, het 3, and het 2 as representative of different isospaces, then their iso multiplication of this one is given with 16, and the iso multiplication of these 2 elements of different iso spaces is 12, then this expression is equal to 4. In this example, yes. Yes.
Excuse me, in what sense are you using the word space here? Because I don't understand.
Because see, to define when we consider cross product.
Cross product.
Yes, classical cross product. We have to multiply the second coordinate of the first vector with the third coordinate of the second vector minus the third coordinate of the first vector with the second coordinate of the second vector. In other words, in the geometry, in one moment, to find some coordinates, we have to multiply not only first coordinate with first coordinate, second coordinate with the second coordinate. Sometimes we have to multiply, for instance, first coordinate with second coordinate, as in the cross product. To find cross product of both vectors, we multiply not only coordinates from one column, we multiply second with third coordinates. And but the different coordinates belongs to different isospaces, because the first coordinate belongs to the isospace with isounit head T1, the second coordinate to the isospace with isounit head T2, the third coordinate isospace with isounit head T3. But when we have to multiply second with the third coordinate, we have to introduce some rules.
For example, if I select different unit for different coordinates, then the units for each coordinate modify the representation of the numbers in that coordinate. That's okay?
Yes,
right?
yes, you're right. We have to make a modification because to get two numbers from one isospace. And this modifications is given in this way, because we cannot multiply iso number from one isospace with iso number with other isospace. We have to modify every one of these iso numbers so that to belongs to one isospace other than these two isospaces, and then to apply iso multiplication. Now it is given in this case. In this case, we modify head 2 here, which is in the first isospace with isounit head T1. We modified this number to iso number with iso number from the isospace with isounit this head T. Then we modify head 3 from the second isospace with second isounit head T2. We modify to iso number from the isospace with isounit head T. And then after we modify to this isospace with isounit head T, we iso multiply them using this isotopic element.
Okay.
The idea to be correct, defined iso multiplication between different isospaces, we have to modify or to map the elements of these different isospaces to one joint isospace, and using this joint isospace to make iso multiplication.
Okay, one coordinate is one space.
Yes.
Okay, thanks.
Okay. So here is given an example when the isotopic elements are given this one. Then the first number head 4, which is from the first isospace with isounit head T1, we modify to the iso number from the isospace with isounit head T, which is equal to 2. Then this number again we modify to the isospace with isounit head T. The iso number which is from the second isospace we modify to the iso number from the isospace with isounit head T. Then we find this iso multiplication. Using that, we are now in the isospace with isounit head T. Then we find the corresponding powers. Using that, we're in this isospace with isounit head T. Here is given as first example, again, head T1, head T2, and head T3. We can consider examples n-dimensional examples. And in any example, we have to modify and to map the corresponding iso number to some joint isospace, and using this joint isospace to make the iso multiplication. Otherwise, it is not the correct defined iso multiplication between different isospaces. So, and now we introduce the following notation. F with index head t key is this function. If we multiply again, we define iso multiplication between 2, 3, iso division. Here, if we consider the application of two functions is defined in this way. And now it is given an example when the function f is this one, the function g is this one. And then the following applications of these both functions is this one, and the applications of the functions g and h is this function. Here is given second, in this example, we have the iso application is this one. The classical application was this one. They are different. This is the iso application, iso result, and the classical is given with this function. This is polynomial. This is a rational function. So now I will move. There are different examples which are given here for different isotopic elements, how we move to the to a joint isospace, and then to find iso multiplication. Now we will define iso trigonometric iso functions. So iso trigonometric sinus from the isospace with iso head tg is this one. For the cosinus, this one. For the tangents and cotangents, this one. Again, we suppose that these isotopic elements are positive. And now we define an additional angle, head theta, jk, which is defined with this expression. Here participates the isotopic element head tg and head tk square. We see that here we have index gk, here gk, k. And here are given the expression with different isospaces. So when the trigonometric functions belongs to one isospace, the isotrigonometric formulas looks as the classical formulas. These are when we have in one isospace. A difference between two sinus, addition of two cosinus, difference between cosinus from one isospace. The formula looks as the classical formulas. But if we consider the one trigonometric function to be from one isospace, head tg, and the other trigonometric function to be from the other isospace, head tk, using the introduced rules, we get this formula, trigonometric formula, which is very different than the iso formula in one isospace and the classical formulas. Because in this, when we have the two different isospaces, it is appear this term. Also in the arguments, it is appear this angle theta jk, which was defined in this way. This formula is very different than the classical formula. Again, this formula for the difference of sinus from one isospace and cosinus from the other isospace, the formula is given this one. Again, participate this angle theta jk, which depends on the isotopic elements head tj, head tk. Here is given the sum of two sinus, but they are from different isospaces. When the isospaces coincide, they are from the same isospace, then the formula looks as the classical. But when this isosinus and this isosinus are from the different isospaces, then the isotrigonometric formula is this one. Very different, because in the classical case and in the case when we have the same isospace, we have not here this element. this element, this theta jk. Here is theta jk in this way. This can be represented in other way using this representation. This one. This is the formula of the difference between two sinus from different isospaces. This is the corresponding formula, iso formula. Again, different than the iso formula when we have one isospace. And the classical formula. This expression can be given in this way. Again, very different. Here participate this vector, this angle theta jk and the isotopic elements. Here is deducted the corresponding formulas for the sum of two cosinus when they belongs of two different isospaces. The formula is this one, very different. It can be rewritten in this way. Here is the formula for the difference between two cosinus, and the formula is this one. And it can be rewritten in this way. Here are given some formulas for one isospaces. They looks as the classical case. So in the classical, when we have one isospace, Tj, and when we have the power 2, we get the their sum is equal to the iso unit element. But when here is given, they belongs to different isospaces. The sum of this iso square is this one or this one. Very different than this when they belong to one isospace, and different than in the classical case. This is different isospaces. When the isospaces coincide, this element is equal to this element, this is equal to 0, and we obtain this term, which is equal to this one. Then this formula and this is a generalization of this formula in the case when we suppose that one trigonometric function is from one isospace and the other trigonometric functions is from the other isospace. Here is given other representation for the, but here the square is not iso square. This is the classical square of isotrigonometric functions from different isospaces, and this square is equal to this one. So next example, the classical multiplication of tangents and cotangents is equal to 1. When we consider these tangents and cotangents from one isospace, it is their iso multiplication is equal to the iso unit. But if they belongs to different isospaces, then their multiplication is this one. It is different when the multiplication, it is given here the multiplication when we have in one isospace, this and this. Here is given an example for the iso square of this iso sinus, iso square of this iso cosinus, and we have, and if we have to simplify this expression, we get this representation for this expression. These are elementary. So inverse iso trigonometric functions we define in this way. Here are given their properties. They are good. Here is given an example when the isotopic element is equal to 1/3. Then this iso arccosinus from 1/2 is equal to p/2. In the classical case, it is equal to p/6. So in this lecture, we saw firstly the isoperpendicular, isoparallel lines, using them we define isoreflections. Then we have defined isosymmetric isopointer for given isopoint with respect to a given isoline. Then we have considered the basic isomultiplication and isodivision when we have elements from different isospaces. Then we have defined isotrigonometric functions, and then we have considered the basic isotrigonometric functions when then they belong from different isospaces, and we see that there are very big differences. And we have defined that the inverse isotrigonometric functions. And using them, in the next lecture, we'll give what is isorotation, representation of isorotation, iso cross product of two isovectors. But for their definition, we have a need of these definitions for isomultiplications between two different isospaces. Okay, thank you very much.
Okay, thank you.
Thank you. Thank you, Dr. George.
Okay, I don't have any specific questions at this point.
I have one question here. I don't know if this is a viewpoint, a correct viewpoint, but in the definition of trigonometric functions, one can start from geometry, and then from geometry one can define all the trigonometric functions. But the other way is the algebraic definition of that functions. That's what one can define like a series, no? Of potence. But in the definition of series, one need to consider the potence of each term, and then I don't know if we need to use here the isoproduct, for example.
So I think that to investigate these terms in the series, firstly, it will appear in this definition. Yes, in this definition, when we use the algebraic definition, there is not any need from isoproduct.
Yes.
Yes, yes. And for the next lecture, I will prepare comparison with the algebraic definition and this definition which was given in this lecture. And we will see that we will get the same using this iso addition between two elements. IJs.
Okay. Okay. Thanks.
Garrett, I don't have any audio from you.
What?
I don't know why.
Okay, that's better.
But now is closest your microphone, Professor Garrett.
Oh, okay, there seems to be a proliferation of ISO units. Does it really make sense to talk about all these ISO units being different like that? Comparing different, a unit is a unit. It seems like it should be a unique ISO unit rather than all these for each dimension ISO unit.
In physical application, yes, but from a mathematical viewpoint, that's what Dr. Georgiev is doing, considering the most general possible mathematical approach.
Oh, so what is an application? Is there an application? That's the question.
Yeah, whenever in physics you consider a specific problem, for instance, the structure of a nucleus. In this case, you need one iso. You can only introduce one iso unit to represent the entire structure. And but however, if you do a nuclear reaction, nuclear fusion, then there may be then necessarily you have a different. In general, you have different iso units because the two nuclei not necessarily are the same. There may be different nuclei, and then each nuclei has its own iso unit. Then you see, then this generalization presented by Dr. Georgiev is mandatory. Sooner or later, it becomes mandatory in physics. For instance, a fusion of two different nuclei, they need necessarily two different iso units.
Yeah, but I wonder if you could use a tensor product, for example, instead of all these different units or some other alternative than all these.
No, that's yes.
Uh-huh.
It
I
still seems
think
to
that
me that these iso units that we're discussing here are just the diagonals of some diagonal elements of some linear transformation.
But,
Yes.
but not in any case is diagonal, because I think that in there are cases in which the matrix is not diagonal. There are elements over and on the diagonal.
Yes, usually this is typically the case when you have two different entities. For instance, proton antiproton annihilation. The two-point function necessarily needs a non-diagonal iso unit. I suspect that in the fusion, two different nuclei will be the same. Namely, you may end up in different in a non-diagonal iso unit.
I worry that my understanding here doesn't advance very much by these examples that seem, aside from the technical details, seem relatively elementary. Like, I'm not. Maybe I'm missing something.
See, the mathematics is not that elementary. You may think in this way. There are different types of nuclear forces. None of them.
No, I'm not speaking of physics. I'm speaking here only of the mathematics.
Oh, I see. Then Dr. Georgiev will answer. Yeah, thank you.
Well, so I think that this is not so elementary, because here I give, in this example, which is on the screen, it is elementary, but in the other examples, I give the obtained computations. But we'll see that lecture after lecture, the mathematics will be difficult, and so on.
I'm just thinking that perhaps much of this could be stated in more general terms rather than in terms of so many examples.
Yes, as it is given in my book, but when I prepared this lecture, my aim was to include many examples to see the differences. And all of these properties which are given, they are given with very detailed proofs in the books.
But almost all of these examples that show differences are almost, I would say, almost obvious from the beginning, that the differences are expected.
Yes.
Yeah, the numbers themselves don't mean anything. They're just a bunch of numbers.
Yes. All books began with ISO number and operation of this ISO number and the properties. But the mathematics is not elementary.
Well, yeah, that's right. So what all we need is the formulas. No one's going to follow all those calculations. So they just give you numbers, and we don't have a picture or anything to go with the numbers, just a bunch of numbers. So I understand the formula. Okay, that's fine. But then the numbers just don't really add much to it, I don't think.
Oh, okay. You have a need of more explanation of the corresponding formula. Okay, and how this formula is deducted.
Okay, well.
Yes,
Yes.
I think that's-
Yes. In the next lecture, there are buffs slides. In one slides with examples, in the other slides, we will see the detailed proofs how these formulas are deducted. And you will see that this is not so elementary.
Perhaps a related question that was, I think, my second question that I asked was whether or not these calculations have been programmed using a computer algebra system, for example, such as Mathematica. These types of algebraic examples in Mathematica would probably correspond to a very simple command. But the definition of the formulas would require specific type of programming for a computer algebra system to implement this. So,
Dr. Page, yes, it's appear big, strong seems to be interested. For instance, apples. There is some nibbling of serious interest, but we are waiting, as I indicated in the preceding comment. We are waiting for the idea of EPR computer. Has not yet.
no, I'm not referring to any type of new computer technology, only existing computer technology that is able to perform symbolic calculations.
Yeah, but
Yes, it is possible, and I propose Professor Santilli to contact with MATLAB research group or a Stefan Wolfram group,
Yes.
which prepare these big packets, Mathematica, Maple, MATLAB, and so on, so that to include some auxiliary function, for instance, iso addition after you put the result directly to be appeared what is the iso addition of two numbers. It is possible, and I think that Professor Santilli has to contact these three research groups and to explain them and to ask them if they agree to be included such symbolic functions, so that after you put the point and vector directly, the computer to compute what is the corresponding equation of the isoline.
if you could send me the contact, the name of those research institutions, I'll be happy to do so. I know that the formulation is indeed possible, but I've not done it very seriously so far. Incidentally, about your question, Dr. Page, the moment you treat computer computation via isomathematics, you automatically have an EPR computer, because that's what you're talking about is the foundation of the EPR computer. So the EPR computer is a computer was calculation based on isomathematics, essentially. Yeah.
Yes, the main proposal by Professor Page is to be included auxiliary functions in these big packets, Mathematica, Maple, and MATLAB, the ISO calculations. So that if you do not know what is ISO multiplication, but after you enter the some function in the packets Mathematica, directly to obtain what the final result.
Yes.
Without knowing what is this ISO multiplication and so on. But if you have a need in the practice to find the ISO multiplication of this and this, using the computer system directly to get the final result. This is possible, and I will send the address so that Professor Santilli to contact.
Thank you. I'll be happy to do. Incidentally, another application is for weather forecast because it's getting more and because of one of the features of the calculation by isomathematics is this very strong and fast convergence of perturbative series for a small, sufficiently small isotopic element. And so therefore, I know there was somebody. I think Dr. Georgiev, we discussed this this application to the weather forecast years ago in one of the meetings, I believe in Greece, if I remember correctly. But then you know, I've been so busy that I have not contacted any weather forecasting company in America. And but in the problem of fast convergence becomes important because now the people die because of lots of people die today. We have lots of people here in Southern Belt exposed to a bunch of tornadoes. So so a rapid convergence of weather forecast may save lives because may give you more precise identification of where the tornado is. This moment we have just a belt. I look at this yesterday night on the TV. Just the weather forecast gave a belt, very wide band of probability where the tornado will hit. But no, but with with isomathematics, that I believe that can be. But I cannot do everything, so it's also up to other scientists eventually to see the advantage of isomathematics and
Okay,
I think it was on the fluid dynamics ideas. Fluid dynamics.
are we intending to proceed with this series in this same way so that we would continue next week with the next presentation?
Yes, yes.
yeah. My suggestion is only that we should have a discussion, 10 or 15 minutes discussion on the for the isotopic element, better on the isotopic element.
Yes, yes, okay,
Okay.
okay.
Now,
Next lecture.
it really is using it with geometric algebra or Clifford algebra directly rather than everything dealing with matrices. You get geometric integration of the elements with the Clifford algebra aspects to it.
Okay, yes, it will be considered. Okay.
Okay, well, I think we've spent more time than usual, or more time than scheduled, but I appreciate everyone's attention and I'll see you all next week.
Yes, at the same time, next lecture on geometry. Okay.
Thank you, Dr. Page. Thank you.
Bye for
Thank
now.
you. See you.